Hey everyone, it's Bradley Bush with another algebra video for you. Today our topic is partial fractions, and we will talk about the big picture. I'll give you maybe 30 seconds background so you can kind of see where we're going. Then we'll do an example for the remainder of the time, and it will deal with a prime non-repeated quadratic factor. So let's go. First, where is all of this coming from? When you're adding fractions, if you remember, you would take two fractions, for example, and you'd add them together. You'd get a common denominator because you couldn't just add them together like they were because the two denominators, the 2 and the 5, are not the same. So you get a common denominator by multiplying on top and bottom by 5 on the 1/2 and by 2 on the 3/5. Then they both have 10 as their denominator, and you can add the tops, and you're good to go. You've got 11 over 10. That's really all we're doing, basically. We just have a few things that we throw on there that kind of change things around. If we're doing the exact same thing, but we're adding rational functions or rational expressions, we have a denominator x minus 4 and a denominator x plus 2. Those are both unique. They don't have anything in common. So to get a common denominator so that we can subtract these two, then we first multiply the x minus 4 by x plus 2, top and bottom, and we multiply the x plus 2 by x minus 4, top and bottom. So we get a common denominator of x minus 2, x plus 4. And then we do some algebra at the top, and we get our answer. So this x plus 4 over quantity x minus 4 times quantity x plus 2, that is now one fraction, but it started out as two different fractions, two smaller, two simpler fractions that were subtracted to get this one. So that's really the main idea behind partial fractions. So what are partial fractions? Well, here's the punchline. When you add or subtract partial fractions, you go from 2, or perhaps more. In this situation, I have 2. I'm subtracting 2 and I get 1. So I've combined them. Oftentimes that's the path you take in algebra. But partial fraction decomposition says I can bet that this has smaller pieces that add or subtract up to make it. And you go the opposite direction. You start with the more complex one, and you break it apart to its little bitty pieces that are then added or subtracted together. So that's why they call it partial fraction, because you're breaking this one whole fraction into a bunch of pieces, or partial fractions. So adding and subtracting goes left to right. Partial fraction decomposition goes right to left. That's it. That's the big picture. So there are 4 different types of partial fraction problems. The 5th one is just a combination of all of them. Today we are doing one that focuses on number 3, non-repeated prime quadratic factors, but truthfully it's number 5 because we throw in there a distinct linear factor, so we throw in a 1. All right, here we go. Here's our problem. Find the partial fraction decomposition of 3x squared plus 17x plus 14. That's all on the top. In the bottom we have quantity x minus 2 times quantity x squared plus 2x plus 4. So the x squared plus 2x plus 4 is prime. We can't factor it. So we really don't have anything in common between these two. They're both factored in their prime form, so we just start. We first need to find all the unique factors. We just did. The first one is the x minus 2, and the second one is the x squared plus 2x plus 4. Are these factors quadratic or linear? Because whether they are quadratic or linear will tell us how we set up our problem. So we can see the x, well, they're both quadratic and linear. The x minus 2, that is linear. So I'm going to put an L below that. And the x squared plus 2x plus 4 is quadratic because we see the 2 on the x. So I'll put a Q by that one. So we have both of them. So our setup, a problem setup, is going to contain both of the types. For the linear, this is the linear term. The linear term, we list the quadratic, or sorry, that's funny. The linear term, we list the factor x minus 2, and then we just put a constant above. So I just use the alphabet and keep going along in the alphabet until I'm done writing constants. So I start with A. So I just put an A up top. So I have my linear factor in the bottom and then an A up top. And then I'm going to add to that. I only have one of these linear factors. So you see it only appears, x minus 2 only appears once. So I only have to have one linear term. I move next to my quadratic term, and I put my quadratic factor in the denominator. And because I have a quadratic in the bottom, I put a linear constant term in the top. So I have bx plus c, and I just chose b and c because they were the next two letters in the alphabet. But I have to have something of this form, constant times a variable plus a constant, because I have a quadratic in the bottom. This quadratic is non-repeating. If you want to know about how to solve a problem where you have repeating quadratic, I have a video that discusses that in my playlist, Algebra playlist. So now we have the problem set up. This is the quadratic term. Now we have the problem set up. We can start combining the right-hand side. The reason we start combining the right-hand side is because we're going to end up comparing these coefficients. And we can't do that until the right-hand side is one fraction, and it's in the form of the left side. So let's combine these two terms. We can't do that until we get a common denominator. So the x minus 2 term is missing the quadratic term, so we're going to put x squared plus 2x plus 4. And what we do to the top, we've got to do to the bottom. So we multiply x squared plus 2x plus 4 on the top as well. And what are we missing on the right? Looks like we have an x minus 2 that we're missing. Now we have to combine all of them, right? Now that we have a common denominator of x minus 2 times x squared plus 2x plus 4, we can combine the stuff that's in the top, and we put it all in the numerator under or over the common denominator. And now we've got to do a little bit of algebra. So I need to multiply that a through each of the terms in the quadratic factor, and then I've got to do some foiling over with my two linear terms. So the x is going to multiply in both of those. The negative 2 will also do that. So let's just see. So a times x squared gives us ax squared. A times 2x gives us 2ax. And a times 4 gives us 4a. The next one, we started out with, let's do the x times the c. We'll call that cx. We'll do the x times the bx, which gives us bx squared. And we have negative 2 times c, so that's negative 2c. And what else? One more. Negative 2 times bx, so negative 2bx. Now we need to combine these together. So let's start with all of the terms with an x squared. So that gives us ax squared and bx squared. Notice I have those here. Let's do all the terms with just an x. Where are all of those terms? We have a 2ax, and we have a cx, and we have a minus 2bx. I have all of those terms here. So I'm just rewriting them, I'm grouping them in a different order. And then all the terms without a variable, I have 4a and negative 2c. I have those two terms right there below. So I just rearrange them. That's it. We're getting closer to be able to compare these sides. That's because that's, again, what we're trying to do, right? We're trying to compare what's in front of the x squared term, what's in front of the x term, and what's in front of the, sorry, what's without, what's left over, what's a constant. So we notice in our squared terms, we've got an x squared here and an x squared in both of them, the a and the b. So we can factor that x squared out, and it comes out. We'll put it behind. So we've got a times b, quantity, times x. We can pull an x out of the pink term, the 2ax minus 2bx plus cx, and that comes out front, or we'll put it in back, and we have all of the constants, the 2a minus 2b plus c up front. And then we just have the constant terms by themselves. So now we're actually ready. We're ready to compare. So the reason we're comparing is because we have two items, we have two quantities, right? Two fractions. We have one on the left, or on the right, and then we have this equal sign in the middle. That equal sign says that the two quantities, the two sides are equal, literally. So we can quickly look at them and say, hey, it's obvious that the denominators are the same. So that means the numerators have to be the same. So what's in front of the x squared term on the left? A 3. What's in front of the x squared term on the right? A plus b. So that gives us our first equation, because we know a plus b, whoops, that should be a b, has to equal 3, or this equation, this equal sign in the middle, does not hold. So we do the same thing with the x. What's in front of the x term on the left? 17. What's in front of the x term on the right? 2a minus 2b plus c. So we know that 2a minus 2b, whoops, plus c has to equal 17. There's our second equation. Now we can equate the last term. So we have 14 on the right, that is without any variable, and on the left we have 14. On the right we have 4a minus 2c. So we know that 4a minus 2c equals 14. Now we have three equations, three unknowns, and we solve for a, b, and c. Once we solve for a, b, and c, we're done. We just write out our answer. So we're getting really close. So as we look at this, I think our first step should be to get rid of the b, because we can get rid of the b in equations 1 and 2, and then we can take that new equation that doesn't have a b and use equation 3 to solve for a or c. So let's do that. Let's get rid of b first. So let's try equation 2. Equation 2, my equations have circles around them. So 2 with a circle, that means equation 2, not just a 2. So equation 2, let's take equation 2 and let's add to it 2 times equation 1. So I've written down my equation 2 already because it stays the same. Now I need to do 2 times equation 1. So equation 1 is a plus b equals 3. So 2 times a gives us 2a. 2 times b gives us 2. Whoa, what in the world? 2b equals 2 times 3 is 6. Now we can add the 2 and we get 4a. The b's cancel. We have plus c equals 23. We'll call this equation 4. We called 2a plus 2b equals 6. We called that 1.1 because it wasn't 1, but it came from equation 1. It was like the next iterate. So we called it version 0.1. So 1.1. So let's take equation 4, which is the one we just came up with, 4a plus c equals 23, and take equation 3, and let's see if we can get rid of one of the variables. If we added them straight up, we wouldn't get rid of anything. But if we subtracted them, we'd get rid of the a, and we'd be able to solve for c. So let's subtract them. So let's take 3 minus 4. So we have 3 already written down. Stayed the same. 4a minus 2c equals 14. And now we subtract 4 from it. Or in other words, let's multiply by -1, and then we can add. So let's do that actual math. Equation 4 is 4a, so now we have -4a. Minus c equals minus 23. When we add these two, we get the 0 for the a's, and we get -3c equals -9. We can see here that we can quickly divide by -3 and get c equals +3. Perfect. We've solved for c. Now if we take c equals +3 and we plug it into equation 3, we can solve for a. So here's equation 3. Let's plug in 3 for c. So we get 4a minus 2. Instead of c, we have 3 equals 14. So that's -6. And add 6 to both sides. And we get, that's supposed to be 14 right there, not 19. We get 4a equals 20. So let me write that up here again. 4a equals 20. Then we can divide both sides by 4. And we get a equals 5. So we're getting somewhere. We have a equals 5. We can then plug a equals 5 into equation 1 and solve for b. Here's equation 1. We know a equals 5, so we have 5 plus b equals 3. We can subtract 5 on both sides. That gives us b equals -2. So I have a, b, and c. Now we can just state our answer. We know what a, b, and c are, right? A, we said, was 5. So we put 5 here. B, we said, was -2. And we have an x. And plus, what's c? C's 3. So there we go. Amazing, huh? We just found that this large rational expression, 3x squared plus 17x plus 14, all on the top, and in the bottom, quantity x minus 2 times quantity x squared plus 2x plus 4, that can be decomposed into two smaller fractions that are added together. And those fractions are 5 over x minus 2 and -2x plus 3 over x squared plus 2x plus 4. So we have our answer. So how could they make this a little harder? Well, they could add repeating quadratic roots, for example. Or they could even add repeating linear roots. But if they added repeating quadratic roots, we would add a term for each of the roots, each of the powers. So this would be the first power. We'd add another term for the second power and another term for the third power. And above, we just keep adding constants in linear form. bx plus c, dx plus c, fx plus g. If we added additional, say I wanted to do another one here, I had a square there, so x minus 2 squared. Then I would, down here, I would have to add another one, and I would say this is plus, and at the bottom I would have x minus 2. So I already have the first power at the very front, and this would be the second power. And I would add another constant. The next constant in line in the alphabet is h. So it can get pretty nasty pretty quick, but you have the tools now to find all of those constants. You just follow the same process that we've done before in this video. Hopefully this was helpful. If it was, please subscribe to the channel, give me a like, and thanks for watching.